So in this video we're going to talk about Sigh Pie, which is the scientific toolkit module for Python. It's sort of ubiquitous or standardized at this point. So this is where it works closely with Numpy, which we talked about in the last lecture. So of course Numpy gives you all the data structures, arrays, contiguous arrays, matrices, and operations on them like vector matrix dot products and matrix multiplies. Vector multiplies, things like that. So SciPy is basically fully operational with NumPy. You can send in any NumPy array or data structure to most SciPy functions and it will operate them on a way that you expect. So SciPy is what gives you all of the solvers and other features that you're used to in MATLAB, like root finding algorithms, optimization routines, filtering, things like that. So, basically this reproduces what I just said. It's a collection of the mathematical algorithms and convenience functions built on top of NumPy. It's organized into multiple sub-packages. We'll look at a few of those. There's no way I could cover all of them. And really, in combination with NumPy and SciPy together, reproduce all of the sort of computational ability of MATLAB itself. That's not strictly true, but I would say in general, between NumPy and SciPy, you can do any type of computations that you regularly do in MATLAB. So a few of the submodules, there are more that I haven't listed here, but just a few if we go through them. So the SciPy special submodules, so these are where all your special functions like Bessel functions and Chebyshev functions and things like that would reside. Into scipy.integrate, this is your numerical integration routines. So your numerical quadrature and other initial value problem and some boundary value problem routines solutions are there. SciPy optimize, this is your minimization routines. Nonlinear least squares, Levenberg-Marquardt algorithms, things like that can all be found in there. Interpolate is just what it sounds like. So this is interpolating functions and other things, Fourier transforms and FFT pack. Signal processing, this is where you have your filtering routines. So your discrete filters, Chebyshev filters, things like that. Linear algebra, so this is a package where you'd have solvers, and in some ways it reproduces some of the solver facilities in NumPy itself. However, this also includes solvers for sparse matrices. And you can get some advantage by using sparse data structures, of course, and so then there's also this SciPy sparse package that includes graphing and solvers and other things like that. There's a SciPy stats package, image processing package, some file I/O. This is not, writing text files. These are for writing sort of binary database type files like netcdf or some of the common scientific data storage formats would be found in there, readers and writers for that kind of stuff. Weave is a utility that's built into Python that allows you to write C++ functions, and you can sort of write the code right in line with the rest of it, and then on execution it'll be compiled into a compiled library, and then you can call it from that. There are other packages that are sort of more modern for this, and we'll talk about some of them if we have time, notably C-types and Swig, and more recently one called CFFI, which can be quite useful for that kind of thing. So this is very useful for speeding up your code. A lot of times we write pure Python code and we can speed it up by vectorized operations in NumPy, but if it's still not fast enough, then we can resort to profiling our code to see exactly where it's slow, and then we can rewrite that part of the code in C or C++ or some other language, and then we can use some library to help us call those that compiled code that we wrote in C or Fortran or C++ from Python itself. So we'll look at a couple of examples here. I mean, there's just no way I can cover all of it. You're going to have to resort to the documentation for that and the many sort of online resources. Much like you could teach a whole class in Python, you can you could teach a whole class on sort of the Numpy, SciPy algorithms within this guy. So, if you want to do numerical integration, in this case, integrate a function. So the first argument to this quadrature method is actually a lambda function. So we talked about lambda functions when we talked about function definitions, but basically this is just a way to inline, and in this case, in the argument list itself, define a function. Right? So in this case, the function is just x squared, and we're going to integrate from 0 to 4, and this returns a numerical integration. So it also returns the error. Of course, there's some round off ultimately. So this returns the answer itself and some estimation of the error. So in this case, the exact answer would be like 21 1/3. So it's very, very close, obviously. It might seem clunky to always have to write this, import SciPy integrate before you use one of these. And of course, you only have to do this once in a script, in a Python script. There's a very good reason for that. I mean, there's a lot of functionality in SciPy, and so you don't want to bring all of the methods into the namespace or into the code every time. There's just a lot of unnecessary overhead. You also might, as we've learned with object-oriented program, you might want to have, common function names like integrate that operate differently on different sets of data, of course. So this is why, it's a very good reason why it's useful to use these namespaces like they do. It's pretty common in Python. So there are many other functions, double quad and triple quad for computing double and triple integrals, of course, fixed quadrature, trapezoid rule, and Simpson's rule for computing, discrete integrals. So here's an example of the SciPy linear algebra package. I'm kind of not doing anything very interesting here, but basically I import Numpy just to generate the random numbers, and then basically a random matrix 3 by 3, and then thankfully that matrix isn't singular, which it's unlikely would be if it was just a set of random numbers, so that then I can take the inverse of that, and of course this is the output here. Also, likewise, I can then take the eigenvalues of that. In this case, they're complex eigenvalues. And so the linear algebra package within SciPy is useful for those kind of operations and other linear algebra stuff. So here's an example of using SciPy Interpolate. So in this case, we have basically a set of values, x and y. X are going to go from -1 to 11 in steps of 1. And then y is going to be evaluated at those locations. It's just an exponential function of minus those values divided by 3. And of course, these are Numpy operations. We know how those work. We've interpolated, we've imported a couple of functions from SciPy, or namespaces, mainly interpolate and integrate. And so from interpolate, then we're going to integrate in one dimension this data, x and y, and that's going to produce a function. So this is actually a function object, sort of like a lambda function, meaning that we can actually call it at given values. And so in the absence of being able to plot that function, because we haven't talked about plotting yet, that's what we'll talk about in the next lecture. One way to compare the interpolated function to the original data is to integrate both of them over some region. By no means, just because the integrals are close doesn't mean that the functions are necessarily close, but that's one way, sort of in the absence of plotting, that we can do this. So that's what we'll do. The first one we'll actually call the quadrature integrate function that we already talked about. We're going to integrate over 0 to 10, and we'll look at the answer here is 2.9, roughly. And of course, then if we actually use Simpson's rule to integrate the data over that same region, then we have something that's also rounds to 2.9. So you can see that the two integrals are in agreement, and therefore, at least for now, we'll make the claim that f is a good interpolation of this data. Okay, so that's another module. So again, we just went over just a few examples, and basically what I want you to take out of this, because there's just no way I can talk about every function that's implemented in SciPy, but what I want you to remember is that essentially, if there's a way you can do it in MATLAB, it's very likely that you can do it in NumPy and SciPy. And so basically, between the two, you have a free alternative to MATLAB. I don't want to, again, don't hold me to that strictly. I'm sure that there's some functionality in MATLAB that's not available in this software suite, but for the most part, the vast majority of common things that you would do are going to be available. In addition to that, you get the full power of the Python language, things we've already talked about, object-oriented programming, which is really not available in MATLAB. Only in recent releases have they added some object-oriented functionality, but it's not complete. It's not what Python is, in the sense that from the very beginning Python was intended to be an object-oriented language. Of course, you can also do procedural stuff, which is exactly imperative programming that you would do in Python and MATLAB. So you can still have that type of programming if you'd like to do that. And there are also some functional. There is a Lambda function implementation. So if you're familiar with functional languages like Lisp, these are key ingredients in that. Essentially, you create lists, and then you have functions that operate on those lists. And so you can almost do some type of functional programming as well. There's more reasons to come. We're going to talk about MATLAB like plotting and other plotting packages. In the next lecture, I mentioned briefly the ability to call C++ and Fortran code directly from Python. This makes it a really attractive feature because, again, you can just profile your code, figure out where it's slow, and re-implement those areas of the code in compiled languages to get great speed up. And another great thing is that you can do MPI. MPI stands for Message Passing Interface, and it is the de facto standard for distributed memory parallel computing. And you can actually do this style of programming, parallel programming, within Python, and that's for sure you cannot do from MATLAB, certainly not for free in any way. And so if you have any interest in this, you should probably look at my graduate course, which I'll be teaching.